In this video, we are going to discuss a disjoint set forest as an implementation of a disjoint set data structure. In the previous video, I explained the disjoint set and its operations. This video lecture is a continuation of the last video. I will provide a link to the previous video in the description below and also in the corner. I ended the previous video lecture with this work to find connected components from a graph. From the previous video, you are already familiar with the three operations associated with a disjoint set. The three operations are make set, union, and find set. I will use the same running example in this video to explain the concept of the disjoint set forest. Let us start. We have discussed one application of disjoint sets, which is finding components from a graph. We haven't yet discussed how we can store these disjoint sets in the main memory of the computer. Also, how can we implement these operations make set, union, and find set? Now we are going to discuss those items. Generally, a linked list representation is used for disjoint sets. Today, we will discuss a little bit more complex data structure than simple linked list. We will use disjoint set forests to store each of the sets in the main memory of the computer. In disjoint set forests, we represent each set by a rooted tree. The root of the tree is considered as the representative of that particular set. We will discuss two heuristics. One is called union by rank, and the other one is called path compression, that helps us construct an optimal disjoint set data structure. Let's discuss how disjoint set forests work using rooted trees. When using disjoint set forests, each tree represents a set. In the tree, the root directs to itself. This particular tree represents the set B, C, E, and H. Similar to this one, another set can be D, F, G, which can be drawn this way. The representative is always the root of a tree, and the representative points to itself. In these trees, each node points to its parent. As a result, it becomes easy to find the representative. Now, if we apply union between these two trees, then we will achieve the following one. We will discuss the algorithm pretty soon, but I am showing an example at this point so that understanding the algorithm later becomes easier. When we combine two such trees using the union operation, we will make one of these tree roots the root of the combined tree. Now, which root should we select as the root of the combined tree? We will discuss this soon. If we want to create an union of these two trees, let's say that F will become the root. In that case, C will become the child. So, at first we will draw whatever tree we have associated with F, which is this second tree. Now we will draw this entire tree here. Now, instead of looping back to itself, since C will become the child of F, basically C will point to F. And this is how we merge these two sets in a disjoint set forest representation. There are a few more items associated with this union, which we will discuss pretty soon. Notice that this tree has a height of 2. This tree also has a height of 2. The combined one has a height of 3. That means when we combine two trees of the same height, we are going to generate another tree which has one more level than any of those previous two. When we have equal heights given and we are applying the union operation, it does not quite matter which one we make the root in the combined one. However, when we will have different heights in the input trees, then it would matter. Let's look at an example where we have two trees with different heights. Suppose at any time point we have this set and another set which only has D and F, where our tree is like this one. In this situation, these two trees have two different heights. For example, this one has a height of 2 and this tree has a height of 1. In this situation, the union of these two trees will be different than the previous case. The target is to make sure that the height of the combined tree does not increase more than the height of the tallest tree among these two. Therefore, we will make C the root and will make F the child of C. So we are drawing in the combined tree C, we have this one as the root, then we will have the exact same tree, that is the first tree, and we will merge the second tree with this given one where F will become the child of C and D will remain the child of F as before. Notice that this tree has the same height as this one. In this combined tree, the set will be B, C, E, H, D, F. All the elements of these two sets. So far, we have seen two situations. In the first situation, we had two trees of equal height and the combined tree had one more level than any of these given trees. In the second situation, we had a tree of height 2 and we had a tree of height 1. In the combined one, we generated a tree of height 2. Notice that our target is to make sure that the height is always optimal. That means as minimum as possible. This gives us the idea of union by rank. In the first situation, when we will have equal ranks, then we will make one of these two trees the root and will make the other tree the child. In the second situation, when one tree has higher rank than the other tree, then the root of the tree with the higher rank will become the parent of the other tree. While rank can be many things, we will use the height as the initial rank of any of the trees. That is, when we will use the make set operation, we will make sure that the height of the newly generated tree, which has just one node, is 0. The rank will be the height of the tree initially. I am referring to the previous video on disjoint sets on this screen. When we will use the make set operation, we will make sure that the initially generated tree has a rank of 0, which is the height of the initial tree. Because this initial tree has only one element when it is created for the first time. Notice that every node has a parent. That is, in the implementation, each node is an object. Let's say that every node is a node object. And inside this node object, there is a reference called P, which is actually the parent of this given node. This node also has a rank. So P is a reference, which is also a node object. Rank is nothing but an integer. Now in our function makeSet, we will have one parameter as said earlier, which is x. Here, x is a node object. That is, in the very initial stage, when a node is created, it points to itself. So x dot p will be x. That means the reference of x is actually kept in the p variable of the node object. Another item is whenever we create the tree, there is only one node. Therefore, the height of this tree is 0. So what we will do is we will set this height as the rank of this tree. Therefore, x dot rank will be 0. And this is our makeSet function. Before writing our union function, let us write our findSet function first, because our union function will use our findSet function. FindSet has one parameter x. This parameter x can be any node of a given tree. The purpose of FindSet is, given any node or any element, we will traverse up to the root and we will return that root, because FindSet returns the representative of a set. If we find that the parent of x is itself, then we should return x.p. Because x and xp, they are practically the same item, because there is a loop here, something like this one. Therefore, returning either x or x.p is good enough. However, if we find that x is not equal to x.p, in that case, we will have to make sure that we go to the root. So we write a recursive function which calls itself, which is findSet, and we actually send the parent of this given x, which is x.p. Now, one thing we should do is we should move upward. And when we are moving upward, we can say x.p, that is the parent of p, is whatever returned by this findSet function. Now notice that we are changing the parent of p in this process. What happens here is this. Let's say that we have a tree with the following nodes: A, B, C, and D. What will happen with this following call? Find set D. That means the user is calling this method findSet with the node D. Now, since this is a recursive function, we can trace this using whatever parameters we are receiving. What we are saying is, if D is not equals to D dot P, because this is what is written in the algorithm, we are replacing X with D. In that case, D dot P is equal to findSet D dot P. Notice that D dot P is actually C. That means from here we are going to another call, which is findSet C. And inside this function we have this code: if C is not equal to C dot P, that means if C is not the root of this tree, then C dot P is equal to findSet C dot P. Notice that C dot P is B. Therefore, we are calling again from here to another function, which is findSet with b. Now we are saying if b is not equals b dot p, then b dot p is equal to find set b dot p. Now b dot p is actually a. So in another call, we have a find set a. Now if a is not equal to a dot p, so this part becomes false. As a result, we will not go inside. Rather, we will directly go to the part where we return a dot p. So we are jumping here to return a dot p. Notice that a dot p is a. So we are returning a via this path. So instead of find set bp, we can replace this by a. So b dot p, that means the parent of b will be a, which already is, but we are reassigning this. So now here we are saying return x dot p, which is b dot p. Again, notice that b dot p is actually a. Therefore, from here we are returning a in this part. As a result, this becomes a. Notice that we said c dot p is equal to a. Meaning is that from c dot p, currently we have b, but now we are saying that c dot p should be a, which is this one. That means we are eliminating this link, and c is directly pointing to a. Now from here we are saying return c dot p. Notice that c dot p is actually a. Therefore, from here we are returning c dot p, which is a, in this function. So we have returned a. Therefore, this part is replaced by a. Now we have said that d dot p is equal to a. That means d dot p, this should have a parent which is a. And of course this link is gone because this was the previous p, and as new p we have this one. Now we are writing return d dot p. Now notice that d dot p is actually a. As a result, this function will return a. That means when we are searching for the node d, a is returned, which is the root of the tree, but in the process all the intermediate nodes in this path will directly point to the root. And this is what is called path compression. Let us get back to our discussion on the implementation. Now we will write our union function. In our union function, there are always two parameters. That means two nodes are given. For these two nodes, we will have to search their representatives. That is, we have to call the findSet function with x, and also we have to call the findSet with y. As a result, we will receive the set that contains x and we will receive the set that contains y. We will use another function named link, which will link these two sets. One set that contains x, the other set that contains y. We are now writing our link function. Link function also has two parameters, but for sure, this parameter is a root node. Also, this parameter is a root node. Given that these two parameters are root nodes, they have valid ranks. If we find that x dot rank is greater than y dot rank, then it means that x probably has higher height. If we find that x dot rank is greater than y dot rank, then we make sure that y becomes the child of x. That means x becomes the parent of y. If this is not the case, that means if either x dot rank is smaller than y dot rank or x dot rank equals y dot rank, then we go to this else part. When we come to the else part, for sure this is what we can do. We can make y the parent of x, because x probably has a smaller rank than y. If x has equal rank, then also we're making the second parameter the parent of x. Now one thing we have to do, if x has a smaller rank than y, then we don't have to change the rank at all. But if x and y have equal rank, then we have to make sure that the rank of y is increased by 1. That is because when x dot rank and y dot rank are equal and we have made y the parent of x, we have actually increased the rank or the height of the tree by 1 level. This is why the root y should have 1 added in its rank variable. Again, this part is our union function. The union function calls another function named link, and this is our link function. The link function at first checks if the rank of x is higher than the rank of y. If the rank of x is larger than the rank of y, then we make sure that x becomes the parent of y. Otherwise, there can be two scenarios. One scenario is x dot rank is smaller than y dot rank. In that case, y becomes the parent of x. In the other scenario, x dot rank is equal to y dot rank. If we find that the rank of x and the rank of y are equal, in that case we have to make sure that the rank of y is increased by 1 because the number of levels increased. Note that if the rank of x is smaller than or equal to the rank of y, then y, which is the second parameter of the link function, becomes the parent. In our examples in this video, when we will merge two rooted trees of equal rank, we will make the second parameter the root of the combined tree, because we are using this specific code. Our makeSet function is provided here and our findSet function is provided here. This findSet method will return the representative node, that is the root of the tree. In the process, it will make sure that every node from x path forward till the root will point to directly the root. We will use the same example that we used in the previous video to find connected components. We will demonstrate how we can use rooted trees to find connected components. So this is the data given. Our target is to find out the components from this given graph G. In our running example, we have this given graph G where we have the vertex set V and the edge set E. If we construct the graph, we'll see that we have two components. One is this one and the other one is this one. We will use disjoint set forest to find out these two components. The first stage is to call the make set operation using all the vertices. And after calling the make set operation using all the vertices separately, we will have a tree for each of those vertices A, B, C, D, E, F, G, and H. Each of these vertices will have a rank of 0 based on the algorithm that we discussed. Now, the first edge is AB. For this, what we will have to do, we have to call union between these two. If we call union between these two and these two trees have the same height, then basically we will make the second node, that means B, the root of the tree. As a result, we'll be constructing this tree. A will become the child of B. Previously, A and B both had a height of 0 or rank of 0. Therefore, this new tree will have a rank of 1. The rest of the trees will remain the same. This was our union A, B operation. Now the next operation will be AC because our next edge is AC. Therefore, we will use the union operation between A and C. Notice that A is in this tree and C is in this tree. All of these trees have 0 rank. When we have two trees of different height, the root of the tree with higher rank becomes the root of the combined tree. As a result, this tree will have the root in the combined tree. And C will become the child of B. Since we have two different ranks in the combined tree, we will have the higher rank. The rest of the rooted trees will remain the same. Let us make some space here. In the examples, we only keep track of the root node of each tree. The values of the rank variables of the non-root nodes do not matter in the algorithm. This is because when we merge two rooted trees using union, we do the merging based on the ranks of the roots only. The next edge we have is DE. D is in this tree and E is in this tree. So when we combine this using union D, E, we will have the following outcome. That is, E will become the root and D will become the child. The rank will become 1, since in the rooted trees of the previous stage had 0 rank. The rest of the trees will remain the same. The next edge is A, D. We use the union operation between vertices A and D. A is in this tree and D is in this tree. Therefore, we combine them. When we combine them, since they have equal height, we take the root of the second tree as the root of the combined tree. Since both these trees had a height of 1, we will have a height of 2 for this newly created tree. The rest of the trees will remain the same. Let us make more space. The next edge we have is A, F. That is, we have to use the union operation for A, F. A is in this tree and F is in this tree. Things will start to become more interesting here. Note that the first parameter here is A, which is in the second level. The second parameter is F, which is in level 0. Basically, for level 0, we don't have to worry much. But for this particular node, when we call the union function, we are calling the findSet function. As a result, everything between A and E should point to E after the union operation is called. Without path compression, we will have this tree where E will become the root because it has higher rank, and F will become the child of E. The rest of the tree is drawn here. But due to path compression, this A will directly point to E instead of pointing to B. Notice that C will remain the same. It will not directly point to E. That is because the union function calls the findSet function with A and F, but not with C. As a result, C will remain where it is right now. The rest of the trees will remain the same in this stage. This newly created tree will have a rank of 2 because between these two ranks 2 is higher. We have only one edge left. That edge contains the vertices G and H. That means we will have to combine these two trees using union. Combining these two trees is straightforward. H will become the root and G will become the child of H, and the rank will increase by 1, so it will be 0 plus 1, which is equal to 1. The other tree will remain the same. That is, after the construction of this particular graph using disjoint-set forest, we will have these two trees. In the first tree, we have A, B, C, D, E, and F, which is basically all these elements in this particular component. In the second tree, we have G and H, which is particularly this component. These are the two final trees we have. This node C never went to path compression. We never needed to compress this one in our union functions. If someone needs to compress this, then just one call using findSet using C would be sufficient. So findSet C will reconstruct this tree as this one. C will directly point to E. The rank of this particular tree will be 2. Notice that although the height of this tree is 1, the rank will not change because we don't change rank for path compression because originally it had a height of 2. But for path compression, we have reduced the height. The rank remains the same as before. I should mention this again. Unless somehow findSet is used on a particular node, that node will not create a compression path. This is our final disjoint-set forest for the given graph. The disjoint-set forest contains 2 rooted trees, indicating that our given graph has 2 components. The nodes in a rooted tree represent the vertices of the corresponding graph component. We will not derive the runtime of this particular algorithm, but I will mention what the runtime is. When we use both union by rank and path compression, the worst case running time is big O of m alpha n, where m is the number of make-set operations and n is the total number of make-set, union, and find-set operations. Alpha n is a very slowly growing function. In any conceivable application of a disjoint-set data structure, alpha n generally has less than or equal to 4 value. Therefore, we can say that the running time is linear in M. That means we can call this complexity superlinear. I hope that the previous video and this current video together adequately explains the concepts associated with disjoint set and disjoint set forest. I have made these two videos for the students of the Advanced Algorithm class that I teach in the Department of Computer Science at the University of Texas at El Paso. Of course, anyone is welcome to watch and subscribe to this particular channel. I wish you a wonderful time. Happy learning!